localization, observables, and modular theory. So please go ahead.
Yeah, thanks a lot, Kasia, and thanks all the organizers for having me here. I realize I'm the last thing that's between the reception, so I should try to be on time, more or less. Before I start, let me mention, so this is joint work with Ivan Romualdo for the most part, and it certainly fits with the topic of the conference, Mathematical Physics and Operator Algebras, although operator algebras will be a little bit in the backseat. And some people have heard similar talks before. It's stuff I'm working on at the moment. So there's something new every week. So also for this one, in comparison to say the talk that some of you attended 2 weeks ago. Okay, let me start like 100 years ago in quantum mechanics, how to describe localization. So where to find something. You defined it in terms of spectral projections and position operators, as we know, right? Think of L2. Think about spectral projections like that. You get probabilities where to find a particle described by such a vector with this formula. So that's something that's textbook quantum mechanics, really. And the main features that we use here, and they have been emphasized by Whiteman in Whiteman axioms, not for quantum field theory, but for localization observables, are simple and easy to write down here. So we look at what we would call a spectral measure, a projection valued measure, a map from Borel sets. It's not easy to handle this. To this curly P are complex orthogonal projections on a Hilbert space. Mapping the empty set to 0, the full set to 1, sigma additive, which has many properties. For instance, it takes intersections to products, as you know, takes unions to such things. They should be Euclidean covariant for us to make sense of localization observer. Okay, so that is very basic. Let me point out then in this line here, these two things are what truly matters. The others are consequences, well, not the covariance, but the intersection and union property, for instance. Or you could also say other consequences of spectral measures are that it's monotone, right? Larger region will be mapped to a larger algebra, that's automatic. Or C denoting the complement if you have two separated things, as I will call them, one contained in the complement of the other, then the projection is dominated by the complement of the other. So this is all well known, and in some sense, this looks a little bit like quantum field theory. So this is like a compatibility with inclusions, as we have in field theory as well, on a different level. And this is a compatibility with separation, locality in quotation marks. So that's also what we have in field theory. Okay, so what will this talk be about? It will be about localization in quantum mechanics, really. So I will put myself in the position to think only in quantum mechanical terms. That means no quantum field theory initially. So we think not of space-time initially, but just on a Cauchy surface, although this might change a little bit as we move along, but that's the idea, right? So as is well known, such position operator spectral measures, they do not like relativity. And you can say this a little more precisely. So if you add some relativistic type axioms, for instance, you talk about space-time localization, Poincare covariance, not Euclidean, and maybe positive energy, then such things simply don't exist. So that's a fact, and I will review that. Many variations of this are possible. For instance, you can talk about positive operator value measures instead of projection valued ones. We heard this a little bit already in previous talks. And it's an old subject in a way, but there's a lot of renewed interest in that recently. So let me quote Terno, Castigliano, and Walter Moretti mostly, who wrote many papers on that. And this is partially the motivation for this talk, because these constructions that are discussed here and that I will actually relate to, they don't talk about stuff I like in particular, namely modular localization. So in this talk, I want to give a general formulation of this localization problem, as it's called, in quantum mechanical terms, but in a fairly broad setting that uses logics and lattices and things like that, that certainly fits various different scenarios. And in particular, emphasize that this modular localization concept that many of you will know from quantum field theory fits perfectly inside it. Typically, it's conceived as something quite opposite and different from the quantum mechanical localization concept. But as we will see, from the right point of view, it's I should emphasize that I'm not saying in any way to properly understand localization and relativity in quantum physics, you should do quantum. Yes, I fully agree with that, and I don't want to give you the impression it wouldn't be like that. But from the point of view of quantum mechanics, you get quite close to structures in field theory automatically, as we will see. Yes, and what's work in progress is that this modular setting seems to talk to this positive operator valued setting as well. And there are interesting comparisons that I partially understand at the moment, but we'll come to that. Okay, so that's the setting. And now let me start the talk by giving you the vocabulary. I want to work in this lattice framework, which is quite general, so I have to introduce a little bit of terminology. Okay, so this is something we have to read through carefully because I will use it all the time. So where do I stand? Let's go over here. So what's a lattice? So just some definition. So it's first of all a partially ordered set with maximal and minimal element. I call them 1 and 0, such that you always have suprema and infima. This is a non-trivial condition, and I will see counter examples and examples as we go along of various natures. So there are geometric ones, analytic ones, probabilistic ones, logical ones. An involution lattice, previously I called this differently, but I learned there's literature on this. And involution lattice is the accepted term. It's a lattice where you have an order reversing involution. Okay. You can think of many examples immediately. And an element A is called complement of B if the supremum is the maximal element and the infimum is the 0 element. So that is not required in an involution lattice. So I learned that logicians like involution lattices if they think of Schrödinger's cat. Yeah? So the law of the excluded middle doesn't hold. Yeah? So you have yes and no at the same time, sort of. Yeah? So that is okay in an involution lattice. But if I say complement, I truly mean complement. The lattice is called auto-complemented if this involution truly consists of complements. And a logic is a little bit better. It's an auto-complemented lattice where also relative complements work, as you would expect. So maybe the only picture I need here. So you have an inclusion A in B. Well, how do you get B back? You take the relative complement, everything in B without A plus A. So that looks trivial, and it's trivial in sigma algebras actually, but that's a condition in general. Yeah, so that's called logic. Good. And I should also be careful to say what does separation mean? To elements separated means that A is dominated by the complement or just the this involution acting on the other element. So that by definition is what I mean by separated, and it's different from disjointness. Yeah, disjointness means the infimum is 0. This is weaker in auto-complemented lattices. In involution lattices, it's just a different statement. And in a logic, it's the same. But so whenever I say separated, think of space like separated. That's an example, for instance. Think of commuting for Neumann algebra. So that's an example. Okay, so we will have to distinguish between involution lattices and logics. So that will be important. And separated means that. Okay, let me walk you through, I think, 6 examples that we will need. The first is very trivial. It's sigma algebras. So sigma algebras are logics in this sense. So these are just sets, you know, and I have all the set theoretic operations. So I have set theoretic inclusion, intersection, union. Maximal element is a full space, and set theoretic complement and empty set. So there you don't need to talk much about that. That is quite clear. A more interesting example of geometric nature comes from space-time. And that has been called by Cassini, calls it the logic of space-time. Yeah? And other people already in the 70s, I dare not to pronounce them. I would be precious help for these Polish people, I think.
Probably Cegła and Jadczyk.
I see. Thank you very much. So yeah, so the logic of space-time that consists of all causally complete subsets of Minkowski space, right? Where the complementation, so let me try to use this here. This causal complement is defined in this way. All points in the Minkowski space that are not time-like to the ones in O and also not in O. So that's the causal complement. And then you have the generated causally complete set as the supremum and infimum is intersection. So that is a logic. Yeah? You have to be careful how to define the causal complement to truly make it a logic, but this works. Different versions don't. So this is one that we will use. And maybe just a little remark here. So because we will compare localization at fixed time and in space-time, you can conveniently take, say, Borel sets. Very curly B is Borel. Although sometimes I think I should take Lebesgue. There are some measure theoretic considerations, but let's not get into it. Yeah, so a sigma algebra at fixed time, you can map into causally complete regions in this way, and this is a logic homomorphism, as this picture tells you. Yeah, that's quite clear. Yeah, so that's one example we will use. For Neumann algebras, of course, form an involution lattice, or for Neumann algebras on a fixed Hilbert space, which is not auto-complemented. For instance, here for Neumann algebras and inclusions, it does not work like that. Yeah, so the relative complement can be trivial for a proper inclusion. Yeah? So this is an example of an involution lattice that's not auto-complemented. Okay, we will not need that too much, but we will need very much. Going back to Birkhoff and von Neumann, the logic of quantum mechanics, as it's called, a fancy name for projections. So this is nothing else but complex orthogonal projections, or if you like to think about it in subspaces, you have a Hilbert space and you look at closed subspaces. So everybody knows how this works. If you take a supremum, well, you put the two spaces together, closed span. The infimum, well, you intersect them, and the complement is, of course, the orthogonal complement. Yeah, so that fits perfectly. Alternatively, you could say, I think about it rather in terms of the projections that project onto these spaces. And then you talk about the lattice of all orthogonal projections. Clearly, orthogonal complement of P is 1 minus P, and P being separated from Q in this lattice means the product is 0. So this is all, of course, old stuff, but it will be relevant to compare with other things. It's also a logic in this case. Yeah? So you can orthogonally decompose, so relative complements work well. Okay, so one lattice that we will need quite a bit is a variation of this guy. Yeah, so you could call it, if you like, the involution lattice of spaces. And I will call it E, and it gets a little index R for the reals. So initially it looks like the example number 4, but then there are differences. So let's take another Hilbert space again, this time complex. That will be important. Up there it could be complex or real, we don't care. And let's look at all real closed subspaces. The convention for the terminology is real subspaces are called straight H. Yeah, I'm not sure if this goes back to you, Roberto, or to somebody else, but this is how it's done. Yeah, so not Hamiltonian or anything like that. It's a real closed subspace whenever you see an H. Yeah? So this guy is an involution lattice. Okay, but I should tell you what the involution is. I will do that in a minute. So first, just the lattice is simply as above, only the real version. So I take the real closed span for the supremum and the intersection. That's clear. But the complementation is different. I take the symplectic complement. That makes a big difference. Yeah, it will be called prime. It's defined not as the real orthogonal, but I times that. Yeah, so that's a symplectic complement. And that makes a very big difference. So first of all, as far as the logical structure is concerned, this is not a complement. It can even happen that H is the same as H prime. Yeah? So that can actually happen quite a bit. Yeah? And so you can have just the same as for inclusions for von Neumann algebras, you can have inclusions of such spaces with trivial relative complement that are proper inclusions. Yeah, so that's just an involution lattice, but it is relevant for the rest of the talk. And I may, of course, think of it also in terms of projections. So if I project onto real space, it's only a real linear orthogonal projection and 2 warnings. So the complement on the level of the projection looks different from what you're used to. E prime, so that is just carrying this over to projections, is 1 plus I EI. It's not 1 minus E, yeah, because it doesn't commute with I typically. And projections being separated, so E less than or equal than F prime does not mean that the product is 0. So this is something you have to. But what is also relevant to know, realize, so these are real subspaces, so in particular all the complex ones are. And if you restrict the whole structure to complex one, you get the old example. So it's a stopper. In particular, the symplectic complement of a complex space is the orthogonal complement. Yeah, so that's. If you want to learn more about inclusions of standard subspaces, let me briefly advertise the new paper with Ricardo. There you can learn quite a lot about it, but we won't touch it too much in this talk. So there's one more example that I learned about only very recently. That's the involution lattice of effects. So effects people like in quantum measurement, I think. Yeah, so for unsharp effects, people in logic also like it. Anyway, so what is it? You take a Hilbert space, you look at positive operators that are also dominated by 1, so operators between and 1 are 0 and 1. And this is, of course, partially ordered, but not a lattice. Yeah? So if you think of B of H, or say, or self-adjoint operators, of course, you can talk about partial order. You can talk about upper and lower bounds, but even for 2 by 2 matrices, you have 2 of them, you find a lower bound, but you might not find an infimo. Yeah? So that's just a fact. Yeah? So this is looks very bad initially. So with the operator order, this is not at all a lattice, but there's a different order that makes it a perfect lattice, the so-called spectral order. Yeah? So if you define spectral order of 2, actually you can take 2 self-adjoint operators if you like. Let's say x is spectrally less than y. This is defined in terms of functional calculus like that. Yeah? So that gives you an order. With respect to this order, this is a complete lattice. You have infima suprema, not just over finitely many, but arbitrary families. So this works exactly as you would like. And it is also has this involution, simply taking x perp to be 1 minus x. So this is a different extension of the complex projections. Yeah? So in a way, you have the complex orthogonal projections. You can embed in the real orthogonal projections or in the effects. Yeah? So these are 2 different directions in which you can generalize, but always compatible with the logical structure. Okay, so this hopefully convinces you that there are lots of such involution lattices around that relate to quantum physics, yeah, on various different levels. And now we will play with them a little bit. Huh? So first of all, you open a book on logic and they have a notion of observable. So let's see what is that. Yeah? An observable, slightly generalized here. What is that? So you define this in terms of a logic, and the logic you should always think of either localization in space-time or in space-time. Could be also on the globally hyperbolic space-time if you like, but these you should think about as localization regions. And Q, this is the target. That could be all kinds of things, but always the structure of such an involution lattice. So an observable is simply a map between the two, satisfying natural properties as you know them from many contexts. It should be normalized in this way. It should preserve separation. So for field theory, it means it's local. And it should be sigma additive like a measure. So this is exactly what you ask. So people call that an observable, and you say it's covariant in case you have a group that acts by automorphisms on these 2 structures. I mean, there's a natural notion of automorphism if that intertwines the 2 actions here, right? So that's a covariant observable. Now, in the following, when we talk about localization, we will distinguish between spatial and space-time localization. Spatial will always mean its initial logic consists of region at fixed time, say Borel sigma algebra, or maybe Lebesgue, or something like that. Yeah? And typically, I will impose Euclidean symmetry, or sometimes translation symmetry is good enough. And when I talk about a space-time localization observable in comparison, then the logic will be all the causally complete regions in Minkowski space, or some other space-time if you like, with Poincare symmetry, or maybe just translation symmetry. Yeah, so that's just terminology. Okay, so let me review an old no-go result. No, I don't know my slides. Let me give first an example. Yeah. Okay, let's look at the case where we talk about the Borel sigma algebra on Rn and the complex projections. In that case, you unwrap the definition and say, see, an observable is nothing else but a projection valued measure. We know that. Covariant observer is nothing but a system of imprimitivity, nowadays sometimes called reference frame or quantum reference frame, but it's just that, a system of imprimitivity. If you want to be concrete, well, take localization in R3. and take the complex projections, and you act with a particular action of your Poincare group restricted to Euclidean symmetries. Here, say, take mass m spin 0, positive energy representation, for instance. In that case, what these Newton-Wigner operators are the, up to technical points, essentially unique covariant observable for this thing. So there's a spectral measure you can integrate, and you get what's called the Newton-Wigner operator. So that goes back to 49, or old stuff. But this is exactly how it fits into this world, and this uniqueness is due to Whiteman. Okay, now let me talk about causality. So let me say what is a causal observable. And I do this in the context of only assuming translation covariance. So suppose you have a translation covariance spatial localization observers, a very long word, yeah. But it means you act on regions in Rn only, thought of as acting at fixed time. You map in such a involution lattice, complying with separation, normalization, and additivity. And you asked a little more now, namely causality. So causality means you need a dynamics, of course, yeah. So not just spatial translation, but also time translation. So that means your RD action becomes an RD plus 1 action. So you add one more direction, the time direction. And this picture tells you what you're asking. So if you have your initial region A here and you pick a time direction in the forward light cone, of course, moving it geometrically speaking up like that, and you look at this causal shadow here, that kind of inequality is what you demand. Yeah? Is precisely what you would, of course, demand in a relativistic theory. Yeah? So it amounts to finite speed of propagation. Yeah? So it in particular tells you finite speed of propagation independent of the time direction in the forward light. Yeah? So that is what you want. Very natural. And one fact you can prove easily, maybe I put it as a little proposition here, comparing space-time with spatial localization. It's intuitively speaking clear, if you can localize even in space-time, then, well, I should be able to do it at fixed time. Yeah? So that's somehow easier. And this is the first sentence. You can do this very easily if you have a space-time localization observable. You just compose it with this embedding of the time zero regions, and that immediately works and gives you something causal for free. So if it's a space-time localization observable, it induces a causal one at fixed time, but it also works the other way around. So that's one of the strengths of this lattice approach. So if you work concretely with operators and so on, you have a scheme, say, for defining a spatial localization observable. It's not so clear how this immediately extends to space-time things. But in this framework, this is for free. And this picture tells you how this goes. So suppose you have this orangey region in space-time in which you would like to localize. You have these little regions at fixed time. You just move them inside and causally close. And, well, you take the supremum. Yeah? And that works exactly like that. Yeah? So that means spatial localization observers that generate space-time localization observers for free. So hence, you don't really need to distinguish too much between the two. It differs a little bit if you impose more symmetries like Poincare. But in principle, the two are very much on the same footing. So now what about their existence? Yeah, so these are wishes. This is something one would like to have on physical grounds. So let's see what we have. So there is a theorem often called Malamens's theorem, and we have a version of that. Yeah? So the version of that is bad news, basically saying in certain instances, this simply doesn't work. So take a positive energy representation of translations on some Hilbert space. Consider as your target lattice here the complex projections as Birkhoff von Neumann. And you act on it, of course, in the obvious way on your projections. Then bad news, there is no causal spatial localization observable. They simply don't exist. Okay. In a way, it's maybe not surprising because we are in a quantum mechanical framework, right? So this is not relativistic, and it tells us if you ask too much relativistic things, it simply doesn't like them. But I have a few more comments. So in particular, this Newton-Wigner thing that they know from from a long time ago, this is not causal. Okay, we know that. Huh? The proof is via analytic properties. Okay, I don't have to go into that. And it similarly holds if, for instance, you look at effects that commute. So there's a version by Paul Bush that does that. So this is quite a robust thing, this no-go theorem, but it certainly does not hold if you scratch that Q is P of H and you look for some other evolution lattice in which you could model your observable. Then the rules are different and one has to see what's happening. Huh? So that's really the point, and I would really like to look at these two cases. So let me look at the case where I look in, so at this case where I look at, I wanted to go the other way, never mind. Where I look at the real projections, yeah? So as the target for my localization observable. So then we have the following proposition. We take, as before, we take this positive energy representation of the translations, acting on our real projections as you would. Take any causal spatial localization observed, we don't yet know if it exists, and compute the constraint. Yeah, so what we have to satisfy. For complex projections, the constraint tells you nothing is possible. Here it gives you conditions of Reschlieder type, if you like. Namely, if you have a normal region that has interior points, and the complement also has interior points, then it must have these peculiar properties that modular people know, of course. H intersected with IH is 0. And H plus IH closed is a full Hilbert space, automatic. And how to prove that? You basically take this Mallerman theorem type proof and apply it to two complex spaces generated by your real one, either by intersecting them down or by generating it. So if you do that and you follow that through and use that these complex ones sit in your real ones as a sublogic, you find modular theory is forced onto you. Yeah? You don't have to ask anything. It's quantum mechanics in a way, but it's automatically there. Yeah? Modular theory, I mean, I will have a brief slide on that, why I call it structure modular theory. This is very much like von Neumann algebras with standard vector. Okay, so if we have that, let's see. Yeah. I can never go back here. This is I can go back. Yeah, so what did I want to say? Yeah, so you should read this theorem as saying, oh, there are conditions also in the case of the real projections on what causal localization means. They don't seem to be as strong as in the complex case, but they are still severe. And there's one more thing that I wanted to add here. Namely, there is a hidden notion of Lorentz symmetry baked in, although I'm not asking for any Lorentz symmetry to begin with. Yeah? And what one can prove is the following. If you have such a representation of translations that allows for such a causal localization observable, just spatial, that has an energy momentum spectrum, right? The joint spectrum of the generators. That needs to be a Lorentz invariance. That one can prove with modular theory things. If it's not Lorentz invariant, then forget about existence of such things. Yeah, so that simply is not possible. It's forced onto you. Yeah, so Lorentz symmetry is also forced onto you. So in some sense, if you want to study existence, uniqueness questions of these guys, better just look at the fully Poincare covariant case. Better look at space-time case even, because you can generate the space-time version from the spatial one anyways. Yeah? So that's the message, one of the messages you get here. Yeah.
If I understood correctly, earlier on when you defined causal, you certainly had a speed limit which was the speed of light.
Yes.
But it could have been slower than that in practice, right? You could imagine that the actual speed limit is below the speed of light.
Oh, it could, of course, yes.
Then, so I'm wondering, well, the full Lorentz invariance comes if the underlying theory has a lower speed limit than light.
So the one I'm asking is the one that's compatible with Minkowski geometry, right? So how this comes in is basically by Borcher's theorem, and you look at half spaces and you know how the modular group acts and it looks like a Lorentz transformation, and like that you get it automatically, really. Yeah? So I'm not saying that it's optimal bound, but I guess you can read from it that it can't be any any slower than that. Yeah, so that should be a consequence as well, I think. Yep. Yeah.
I seem to remember there's this related theorem by Borges on the energy momentum.
Yes, I think I remember only very vaguely. There is probably that's very true. I don't know the details at the moment. Certainly not in such a setting. So in some sense, we are playing quantum mechanics and discover, oh, there is field theory. Yeah, so so there is Lorentz symmetry, for instance. Yeah, his setting was certainly without Lorentz symmetry. Otherwise, it's trivial. I'm not quite sure what the setting was, but I should check it. Could be related. Gent. Could be, yes. It might be interesting for comparison, but it's not difficult to prove like this. Yeah, so this is okay. Let's move on. So where was I? If you now want to study these things, you should better be at the strongest level, namely Poincare covariant and space-time. That just makes sense. In these messages. Oh yeah, now I had this brief slide on standard subspaces for those that don't know it. This is always a gamble if people know it or not. So let me go through this very quickly, yeah, because many people know it. Okay, so a real subspace of a Hilbert space having these two properties, a closed one is called a standard subspace. And what do you have to know about a standard subspace? Well, any standard subspace comes with a symmetry, namely one parameter group, modular symmetries, and an anti-unitary involution, J. So this is exactly a Tomita-Takesaki modular theory, which you don't need von Neumann algebras for that. The one parameter group preserves the space. The involution maps it onto the symplectic complement, and both of them define H uniquely. That's what you need to know. Yeah. And this is used a lot in von Neumann algebras and algebraic quantum field theory, of course, as you're probably all aware. Yeah, so these are the things that we will look at a little bit. I mean, one point I would like to emphasize, which I find interesting here, if you think about localization, even in a quantum mechanical setting, you will talk about modular theory if you look at it from this angle, and there's another angle which will also tell you you should look at modular theory. Yeah? Okay. Let me make a brief remark on that, how that works in 1+1 dimensions, simplest case, particle on a line, one spatial, one time direction. Okay, so space-time localization in 1+1. Of course, I have a positive energy representation around. Suppose I have some covariant space-time localization observer. The idea is, can I get an understanding for what that really is? Yeah? Can I maybe even compute it? Yeah? If it's unique, I can compute it. If it's not unique, forget about it. Yeah, so here I can essentially compute it. And take this particular region, which you all have seen before, this wedge, yeah, cause a completion of a half space. So in that case, so people who know this modular stuff well will see quickly how that works. If you have an irreducible representation, so you think of a single particle situation, then this one parameter group that is attached to the localization in this region here secretly is just a boost group. And the conjugation that maps the space onto the symplectic complement is up to assign possibly the TCP operator of the representation. So that is coming from Borcher's theorem, for those who know that. This sign up here means the space could change by factor I or not. Yeah, so that is something that you cannot rule out. But in principle, the main message is you can compute. Yeah, so you can write that down, and if you have an explicit representation, these are operators you can write down explicitly. Yeah, so you don't have to guess what they are. They are just there. That's exactly what I said here. So essentially unique, if you look at a one particle situation, you can compute them. And from here, you can then say, well, what about localization in an interval? This is more complicated because it doesn't have natural Lorentz transformation fixing it, but you can make a maximal choice, namely the maximum that fits with intersection properties. Then, well, you don't get explicit formulas, but you can do numerics. So for instance, Daniela and collaborators, they have numerics on what these things look like. Yeah? So it's well defined and it's a unique maximal choice that you. Okay, so that of course is very much for quantum field theory people this sogenannte Wichmann property, that in modular localization is the starting point. So if you know quantum field theory, it's very natural to take it even as a definition. Here it's an outcome, but so let me connect to this modular localization work by Bonetti, Guido Longo. So if you just define your spaces from the representation in this way, with an analytically continued boost and a TCP operator wedges, and then you make a maximal choice for bounded regions, that works. Yeah, so in other words, this Bonetti-Guido-Longo map, this I don't go into all details, that is a space-time localization observable and up to natural choices unique. Yeah, so you don't have to know the quantum field theory structure. It's just forced onto you. Yeah, so if you look in this lattice, there is no other choice up to wiggling around with maybe making it a little smaller locally. Yeah, but on wedges, this is essentially fixed. In two dimensions. There's more freedom in higher dimensions. And here I should cite Vincenzo, who worked on this question. Yeah, so what about uniqueness question of such an observable in higher dimensions? The geometry is more complicated. You have many wedges. Yeah? And if you, in that case, you can have such an observable that transforms covariantly under two different representations. They might differ by Lorentz symmetries. So that's something that Borg has looked at. And Vincenzo has a kind of uniqueness result. This works in 4 dimensions and higher. And he has a so-called modularity assumption. It's a condition on a representation that you can explicitly say in terms of phenomena algebras. And if that is satisfied, then this identification holds. That means for localization in wedges, you have no choice but to take the geometric one. This does not always hold the assumption, but it holds, for instance, for scalar representations. It doesn't hold for higher spin in general. But so in general, we don't fully understand uniqueness, but existence we certainly have, and we have somehow natural choices. Okay, I should.
You need that to pi in the Lorentz.
I didn't say how I scale my Lorentz transformations, but yes, so I scale them in such a way that it's what you think it is. Yeah. Yeah. Okay. 2 more points I wanted to make briefly. So first of all, now you would like to interpret this maybe tentatively as a localization probability, because that's where we started with. Yeah. And here, so what is the natural idea to do? Yeah, so you take such a thing, yeah, so like such a modular localization observable, you take these projections, you evaluate in a state, take norm squared. Yeah, so maybe one should look at this as a probability to find a particle somewhere. Maybe, yeah. But you quickly find a problem because this is not a measure. The problem, so measure means additive in terms of numbers, of course. Yeah. So if you have 2 separated regions and you add these probabilities, and you wonder how does this compare with the probability for the union? So that's a competition between the sum of these projections and the generated one. Well, this is a projection, of course. Yeah, it's in a projection lattice, but that rarely is a projection. Yeah, it's a sum of 2. So it will be a projection if and only if these guys have 0 product and this is not compatible with standard subspace. So that won't happen. Yeah? So this is not truly a measure, but it's in some sense not far off. So what you can do is you can prove a cluster theorem for standard subspaces. And that tells you, you want to estimate this mistake here. Yeah? So the difference between the sum of the 2 projections and the generated one. And you can prove a cluster theorem that is analogous to a cluster theorem in quantum field theory. And by that you show if your representation has a mass gap. So suppose you talk only about particles with a given fixed mass m positive. And if your 2 regions here have a distance d, then this product, the norm of this product is at most e to the minus m times distance. So it's exponentially suppressed. And that estimates the norm difference on top. Yeah, so if you take them just a little bit apart on atomic scales for electrons, it's perfectly additive, you could say. Yeah, so yeah, so that implies that. So it's almost additive. Okay, still mathematically speaking, not a measure, of course, but it's something. Yeah? I'm running a little bit out of time, I'm afraid.
You started 2 minutes past, so you have 5 minutes.
Okay. So because I wanted to, I have a conclusion and an outlook. Yeah. Yeah. So conclusion is basically wrapping up what I said so far. So one point that I wanted to emphasize that for these localization observers, you can formulate this in this lattice or quasi-logic. It is a different word for involution lattice framework, which allows for a lot of flexibility, and it has some advantages. For instance, when you want to pass from space-time to spatial localization and vice versa. It's something you cannot easily do in different frameworks as far as I know. You can look at the classical case, Birker von Neumann, and you find, well, this is not possible. It's not causal. Yeah, there's a conflict. But this is not true for other lattices, like, for instance, for these real ones, which are, of course, suggested once you know modular theory, but you can rediscover it this way. It automatically leads you to standard subspaces, and you find some essentially unique solutions to the problem. So it's really the drastic opposite of what you find when you look at complex projections. Not only do they exist, but up to natural choices, they are unique. Yeah? So what can you do? Yeah? So it gives you a motivation for modular localization. You don't have to assume any quantum field theory knowledge. It just rolls out of the game. Yeah. Of course, as many of you know, this is exactly a one-particle localization structure for quantum field theory. So once you have that thing, you can build a quantum field theory on top of it. So that you can do. And maybe to finish, I wanted to make some remarks on a different choice. Yeah. So instead of these real projections, you can also look at effects. And that's what people do a lot when they talk about unsharp measurements and so on, positive operator valued measure and that. Yeah. So that's a different generalization of complex projections. Yeah? You could also take both together, but I haven't done. So if you do that, so there do exist positive operator valued measures, denoted X here, that satisfies some weaker form of causality, namely only in terms of expectation values or so, if you want to phrase it like that. And they are delocalized in the sense that if you ask for probability to find a particle in some bounded region, this is never one. So there's always stuff outside. Yeah, so in this sense, they are delocalized for any bounded A. So this goes back to Terno, and then the one by Terno, it was more in physics language, but Walter Moretti made rigorous proofs for that. And also Castrigiano has worked in that direction. So there are many nice developments in this direction. I wonder if that fits also into this involution lattice picture with spectral order, because that would immediately give you space-time localization too. Work in progress in 2 weeks, I know. So that is one thing. And maybe more interesting, here I just say, these exist, but where do they come from? They also come from quantum field theory ideas. They come actually from the energy momentum tensor. Yeah? So that is the idea how this is done. So maybe just as a final thing to show here. So these observables from Terno and Moretti et al. So they are built from field theory input. So you take your energy momentum tensor, you can look at, well, this is like a boost operator. Yeah? And this boost operator, it comes as a moment of this positive operator valued measure. That's how it comes about. Yeah? And if you that sandwich the Hamiltonian, yeah? If you sandwich it between these energy damping factors, well, this is of course expressible in terms of modular data, that is very much behind this observable. Yeah? So here it's not so much about the projections onto these spaces, but about the internal modular structure, I think, or on this level at least. And I'd like to understand how that fits together, these two different approaches. Both use the same, well, not really the same, but related tools, and both try to talk about the same physical ideas, namely localization, and under investigation. Let me stop here. Thanks.